The Defense Advanced Research Projects Agency, a research arm of the U.S. Department of Defense, and NASA are setting their sights on a type of rocket engine that could be the holy grail for quickly and safely getting humans to the red planet. The first tests could occur as soon as 2027, according to a Tuesday news release from the space agency. A rendering from Lockheed Martin of the AGM-183, a air-launched rapid response weapon, ARGW, which had its second consecutive successful test on Tuesday. U.S. and NASA. The U.S. military and NASA sought to develop this type of technology in the mid-20th century, but the program stalled. Now, the initiative is gaining new traction in the modern era as the Demonstration Rocket for Agile Cislunar Operations, or DRATO, program. Research into nuclear thermal rocket engines by NASA began in 1959. A key program in the 1960s, called the Nuclear Engine for Rocket Vehicle Application, even sought to demonstrate the technology in space, but that never came to fruition. Funding for NERVA, however, decreased in the late 1960s, and the program was canceled in 1973 before any flight tests of the engine took place, according to the space agency's website. NASA sending humans to Mars. These days, NASA has renewed interest in sending humans to the red planet. The space agency's Artemis program, which had its inaugural uncrewed test flight to the moon last year, directs the space agency to return humans to the lunar surface as a stepping stone for eventually putting the first humans on Mars. Powerful nuclear thermal engines. As the name implies, a nuclear thermal engine would rely on a nuclear reactor, using a process called atomic fission, in which a neutron slams into an atom to rip it apart, setting off a powerful chain reaction, to heat propellant and provide the thrust needed to propel a rocket through space. The nuclear fission process is better known in the public consciousness for its role in energy production, and NASA previously signed a deal with the U.S. Department of Energy to research its applications for space travel. The reason why NASA is developing nuclear rocket engines. NASA is developing a nuclear rocket engine for a multitude of compelling reasons that underscore the immense potential and advantages this technology holds for space exploration. Firstly, a nuclear rocket engine can provide significantly higher thrust and propulsive power compared to conventional chemical rockets. By utilizing the immense energy released by nuclear reactions, these engines can propel spacecraft at much greater velocities, enabling faster and more efficient interplanetary travel. This enhanced propulsion capability opens up a realm of possibilities for exploring distant destinations within our solar system and even beyond. Another crucial factor motivating NASA's pursuit of nuclear rocket technology is the ability to drastically reduce travel times. Enhanced payload capacity. Furthermore, a nuclear rocket engine has the potential to enhance payload capacity. By harnessing nuclear energy, these engines can offer a higher thrust-to-weight ratio, enabling the transportation of larger payloads and scientific instruments. This opens up avenues for more sophisticated and ambitious missions, such as the deployment of larger space telescopes, robotic explorers, or even human colonization efforts. The ability to carry more equipment and supplies on a single mission would revolutionize our approach to space exploration and expand our scientific capabilities. Safety considerations are also a significant driver behind NASA's pursuit of nuclear rocket engines. Conventional chemical rockets require vast amounts of volatile propellants, which can pose significant risks during launch and in the event of mishaps or accidents. In contrast, nuclear propulsion systems utilize controlled nuclear reactions, which can be designed with multiple layers of safety mechanisms and fail-safe features. Although safety precautions are of utmost importance, it is worth noting that the risk of a catastrophic failure or explosion is greatly reduced compared to chemical rockets. Finally, the development of nuclear rocket engines aligns with NASA's long-term vision of establishing a sustainable human presence beyond Earth. As we venture farther into space and aim for crewed missions to Mars, for example, the ability to transport large payloads and accelerate travel times becomes crucial for sustaining human life and conducting meaningful scientific research. Nuclear propulsion systems have the potential to revolutionize space exploration, making it more accessible, efficient, and economically viable in the long run. NASA wants to send astronauts to Mars, and they could do it with nuclear-powered rocket engines. Nuclear thermal propulsion (NTP) systems aren't new, but they could significantly reduce travel times and carry greater payloads than today's top chemical rockets, giving humans a great chance of exploring deep space. Here are 6 things you should know about nuclear thermal propulsion. 1. NTP systems are powered by fission. NTP systems work by pumping a liquid propellant, most likely hydrogen, through a reactor core. Uranium atoms split apart inside the core and release heat through fission. This physical process heats the propellant and converts it to a gas, which is expanded through a nozzle to produce thrust. 2. NTP systems are more efficient than chemical rockets. NTP rockets are more energy-dense than chemical rockets, and twice as efficient. Engineers measure this performance as a specific impulse, which is the amount of thrust you can get from a specific amount of propellant. The specific impulse of a chemical rocket that combusts liquid hydrogen and liquid oxygen is 450 seconds, exactly half the propellant efficiency of the initial target for nuclear-powered rockets, 900 seconds. This is because lighter gases are easier to accelerate. When chemical rockets are burned, they produce water vapor, a much heavier byproduct than the hydrogen that is used in an NTP system. This leads to greater efficiency and allows the rocket to travel farther on less fuel. 3. NTP systems won't be used at launch. NTP systems won't be used on Earth. Instead, they'll be launched into space by chemical rockets before they are turned on. NTP systems are not designed to produce the amount of thrust needed to leave the Earth's surface. 4. NTP systems will provide greater flexibility. NTP systems offer greater flexibility for deep space missions. They can reduce travel times to Mars by up to 25% and, more importantly, limit a flight crew's exposure to cosmic radiation. They can also enable broader launch windows that are not dependent on orbital alignments and allow astronauts to abort missions and return to Earth if necessary. 5. NTP systems were developed with support from DOE. NTP is not new. It was studied by NASA and the Atomic Energy Commission, now the U.S. Department of Energy, during the 1960s as part of the Nuclear Engine for Rocket Vehicle Application Program. During this time, Los Alamos National Laboratory scientists helped successfully build and test several nuclear rockets that current NTP designs are based on today. 6. NTP systems are focused on using low-enriched uranium. DOE is working with NASA to help test, develop, and assess the feasibility of using new fuels that require less uranium enrichment for NTP systems. This fuel may be made using new advanced manufacturing techniques and can potentially help reduce security-related costs that come with using highly enriched fuel. As we delve deeper into the mysteries of space, NASA's pursuit of a nuclear rocket engine promises to be a game-changer, propelling us toward a future that was once the realm of science fiction. Imagine a world where astronauts soar through the cosmos at unprecedented speeds, where journeys that once took years are accomplished in mere months, and where our reach extends to the farthest corners of our galaxy. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.